Good morning and welcome to NASA Langley Research Center and the Office of STEM Engagement's third webinar in our series of webinars for First LEGO League Challenge. I would first like to remind you that this is the third webinar, so if you would like to watch the first two, they are still on the YouTube channel that you can rewatch as many times as you would like. And our fourth and final webinar in the series will be on Monday, October 29th from 4 to 4:30 p.m. Eastern Time. And you can also find that on our YouTube channel. But now let's get started, and I'm very excited to welcome you to our webinar today, which will be on what types of people study and work on human spaceflight here on Earth. And today we are delighted to have two guest speakers with us today. We have Ryan Norman and Hillary Blakely. Ryan is a radiation physicist here in our research directorate. He models the risks due to space radiation exposure, including the risk of cancer, cardiovascular disease, and degenerative diseases of the central nervous system. All of these are possible negative consequences of exposure to the radiation environment of space. And Hillary is an aerospace engineer in our engineering directorate. Her role has been to turn Langley scientists and researchers' visions into hardware reality that is ready for launch. Over the past year, she has been dedicated to advancing a new heat shield technology that will one day help get humans to Mars. Welcome, and thank you both for being here today.
Thank you.
The floor is all yours.
Appreciate it.
Okay, I guess I'll start. I'm Ryan Norman. I am a physicist. So my training is in how radiation interacts with materials and the human body. So space is filled with a low intensity, high energy background of radiation, and that radiation is detrimental to the health of our electronics and, more importantly, our astronauts. So I try to create models of how that radiation changes as it interacts with materials in the spacecraft or the human body, and then understand how that impacts the systems of the human body, whether that's through the possibility of cancer or other negative health consequences. I know there was a question on our education. So I have a PhD in physics from Worcester Polytechnic Institute, and then I have a Bachelor of Science in Physics also. I'm from a fairly small town in Wisconsin originally. So, you know, for all you kids out there who aren't near the big cities and don't think you have access to everything you need to make it to wherever you want to be in life, you know, if you have the drive, you can get there. How about you?
So hi guys, my name is Hillary again, and I have the pleasure of being an aerospace engineer here. And so my role is usually to come in and take all the incredible science and research that people like Ryan are doing and figure out how to get these concepts and ideas and actually get them into space where we can start taking these measurements and doing what we need to do to be able to eventually get humans there as well. So while I don't work directly with any of the astronauts, my job has kind of been the background of, all right, so one day, yes, we want to get humans to Mars, to Moon. They're already in space now. How do we get them further into space? And I kind of have the role of, all right, let's back up and figure out what we need to do to even get the humans there in the first place. So I've gotten to work on a number of different, like I said, science experiments, an atmospheric monitoring device that is now mounted on the side of the International Space Station. My last project was on an abort system for our new big space launch system, the NASA's new rocket, making sure that during flight, if anything goes wrong, we can still abort and get the astronauts to safety. And now, as was mentioned, I'm working on a heat shield technology that will someday get humans to Mars. And all of these projects have been vastly different. And that's one of the really fun things I think about being an aerospace engineer is that, especially at a research center, you never know what you're going to be working on, what your next project is going to be. I mean, between atmospheric monitoring and humans to Mars, there's a whole range of things that we can get to do and play with. And so a bit of my background is that I graduated from the University of Virginia with Bachelor's of Science in Mechanical and Aerospace Engineering and also Studio Art. So that's kind of been the fun part of my job, is getting to combine those two loves and get to do kind of more of the design aspect of engineering and taking, like I said, the science and kind of say, okay, you want something that will measure this. Okay, well, how do I actually make that happen and get to design from the ground up concepts that will house his science experiments? So it's fun to get to work back and forth on that. And I would say I am from Virginia Beach, Virginia, and didn't know that I really wanted to be an engineer, or I knew I loved space. I knew I loved everything about the idea of looking deeper into our solar system, and wanted to look through telescopes any chance I got. Wasn't sure how to actually get to work in this field until high school, where my physics instructor said, you really seem to like kind of that idea of how things work, and what's the logic behind the universe, and kind of figuring out those formulas and playing with that. And he encouraged me to take a look at engineering, and now we're here today.
That's cool. So some of my path, I never really necessarily wanted to work at NASA. Of course, if given the opportunity, I took it. I actually happened into my research field completely by chance. I emailed all my physics professors when I was an undergrad, asking to do some research. One of them responded. He thought I was somebody else. I showed up for my interview. He thought I was a computer tech and sat me down at his Apple computer. I'm a PC guy. And asked me to fix his printer. And I thought this was some kind of odd test.
That sounds like an engineering test that I would get.
So after I fumbled with it for a few minutes, he figured something was wrong and asked me what was I there for. And I said, well, I'm Ryan Norman. I'm here to interview for the research position. And I think, I can't be certain of this, but I think he felt guilty for doing that to me and just gave it to me. So
that's a great story.
So that's what started me working in space radiation. I was working on the particle physics as an undergrad, and I kept working with him as a graduate student, got my PhD underneath him. And all through that time, I was doing research of application to NASA. And so, all along the way, throughout my education, I really thought I was going to be a professor of physics. That was at least what I thought I wanted to do research on cosmology and understand, the basic drivers of our universe and how it's formed. And, I ended up being a nuclear physicist and working on space radiation. And now I work in understanding biological risk from that space radiation, which is a complete departure from my training. And so one of the cool things about working at NASA, I think, as Hillary said, she gets to work on lots of different things. Additionally, you get to try to do new things that you've never done before.
Oh, yeah. You don't get to, you sometimes have to.
Yeah, there's always that part. Job's a job, right? It's not all fun and games. But you get the ability to move out into other areas. And those other areas can be not what you thought they were going to be. Even 5 years ago, if you would have said I was going to be working in understanding biological risk, I would have said, no, I won't. That's not my plan. That's not what I want to do. So it's fun because you never know what's going to be around the corner. You never understand. You never really know how things are going to work out for you. And you have to be open to all those different types of opportunities that are available. Yeah,
that's something I feel like, as after what I said and listening to you, one thing that I would always tell anyone who's looking to pursue a type of career like maybe we have, to not just limit yourself to what you think you should do. Don't be afraid to follow your passions, follow what you find interesting. I mean, I don't use my art degree all that often in my field right now, but it gave me that kind of leg up as being able to advertise myself as a designer and an engineer, which I think has really led to great success in my career, in my work. And just knowing that you have that passion for space or for human space, like, that's great. Don't ever give up on that. People are going to say, I wanted to be an astronaut since I was in 5th grade. I went to the library and checked out a book on the solar system and spent hours staring at pictures of Jupiter's red spot and Saturn's rings. I came home, I was like, Mom, I want to go there someday, and pointed at Jupiter. And she just kind of did the, like, okay, sweetie, good luck with that, kind of thing. And by the way, my parents have been very encouraging of my career so far. But as a 5th grader, I wanted to be an astronaut, and that was kind of such a far-fetched thing, but I never let go of that kind of all throughout high school, even if I wasn't sure I was going to be an engineer. Even through my hard days of engineering at college, I just kind of held on to, okay, what is my ultimate dream? What would be something that I'm very passionate about? And I'm not going to just give up because I'm having a hard semester or something like that. And for me, that was getting to space, which has been so neat to have that kind of way up here dream and all the steps that I've taken to get there today. Because right now, I think, don't get me wrong, if I had the chance to go to space, I would definitely go. But I find it so neat, the things that I get to work on now are the things that are advancing other people getting to space. And they can't get there without the work that I'm doing. So it's kind of one of those follow your passions, follow your dreams, and you never know where you're going to wind up working on all sorts of different ideas, different options. My art degree, one time we had to, we were sending a satellite up and we had to paint it in, I think, a radiative silver. And I asked if we could like paint designs on it, and they're like, okay, sure, go for it. We're gonna paint over whatever you paint on it, but you can give it a shot from the beginning. So it's not just engineering, science, research, but it's always kind of that blend of the ideas and blend of what people are passionate about. That's what really drives, especially the people that work here at NASA Langley Research Center, is everyone is so passionate about what they're doing. And that's what pushes that technology. You can't just say, okay, I'm going to come in and do my job and go home. It's I want to know what that next thing is, where we can send humans next. What's the next big goal, the next big technology breakthrough? And pursuing that and pushing that forward, I think, has really been what's driven us and driven our center all the way since for about 100 years now.
That's right. Yeah, so I think one thing I would like to impress upon everybody is, and you mentioned this, was that there's more to being an engineer or scientist than math and science and engineering.
Those are important too, don't get us wrong.
Top of the list, don't get me wrong, but I spend a lot of my day communicating. I spend a lot of my day writing. I spend a lot of my day talking with people and trying to help understand what they're telling me so that I can translate that into something useful that I understand. And so being well-spoken, being well-written, especially as a scientist, one of my major parts of my job is to produce research papers. So all of the time you guys spend in English class learning to write properly and articulately is really, really important to me as a scientist, because the way I communicate my research results is through journal articles and through writing, and then going out to conferences and presenting those results. And so being able to tell the story of your research, being able to tell the story of what you do is as important as the work, because great work is done all the time, but if it's not disseminated to the rest of the world and is not used, it can't be implemented and make a difference. That's a big, big part of at least what I do, and I know a lot of what you do.
That's so true. That's so as an engineer, I'm not as much into the science world or presenting at conferences or writing papers, but that writing still plays a huge role. For example, actually later today, I will be performing a test in one of our high pressure systems labs, and I'm working with a lot of pressure, with a lot of nitrogen flowing through a system. And if I haven't written that test procedure well, and the technicians around me don't know exactly what we're supposed to be doing next, some of those things could explode. We actually have to shut something called a bomb curtain in front of it so that if anything explodes off of our test setup, we don't actually injure people. But yes, writing, sorry, real stuff happening here, you guys. Writing test procedures, that you need to be clear when you're communicating. And I would say that's one of the things that surprised me as an engineer, being able to actually work well as a team, wanting people to come together and understand what you're saying, being able to speak to not just engineers and technicians, but also your project management to explain to them why we need this test. Why should they put funding towards this test? Why should they put effort towards it? You need to be able to kind of communicate that. And so it's one of those unexpected skills, I would say, for science and researchers to be able to write and talk well. Not only that, but like I said, we're doing things that we're so passionate about and so excited about. So obviously you want to be able to tell everyone what you're working on. And sometimes you have classified projects, but more often than not, because NASA's with the government and everything that we do, we want to share with y'all. we have exciting things going on, and we want to be able to tell not just the people above us at Langley, our bosses, but our family, our friends, students. We want to be able to communicate well what we are trying to achieve, and be able to share that passion and that excitement, so that one day, hopefully, you guys will be the ones sitting in these seats telling us what you're working on.
I think another really important thing about engineering and science and research, especially in the real world, once you're out of school, is your ability to fail well. When you're working on very hard problems, you spend more time being wrong than you do being right, which is very different, at least in terms of my education, right? You know, you're given problems in class and you know there is a solution. You just have to figure out what it is, because teachers give you problems that have answers. Whereas every day I work on problems where I'm not certain there is a solution. And so you have to be very methodical, you have to be very patient, and you have to be willing to be wrong. And then take the criticism when you think you're right and somebody stands up and says, actually, I think if you look at it this way, or you did this analysis correctly, you're wrong. And having the humility and the perseverance to be like, oh, well, that happens, time to move on and try something else, or attack this problem in a different way. So all those things you're learning, I think, in these sort of robotics type problem solving teams, I think is invaluable in learning to apply what you're getting out of the classroom and through your research to a real problem, and seeing the steps that are involved in attacking things systematically, and understanding when you fail, how to make it better, because that's where real learning happens, is in those failures. There's famous sayings all the time, you don't really ever fail, all you do is learn. And that's really what I spend all my day doing. I tell my kids, who are the same age as you guys out there, I spend all day being wrong. And when I'm right the first time, I get very, very nervous, because I'm convinced that I did something wrong then. It's only when you've been wrong a few times that you can have some confidence being right at the end of it.
And I'm sure you guys have experienced that as you're trying to work on your robots and build up. I would say the flip side of that is even, especially for engineering, being comfortable with being uncomfortable. I'm sure you guys have experienced this. You get a set of requirements as to what your robot needs to do, and then you're just kind of sent off to create that. And that's really what I do in my day-to-day jobs. And we'll say, okay, we need a platform that is this tall and someone can work under it and it'll rotate 7 degrees and be able to integrate these 2 spacecraft. And I think, anything else? And they're like, no, go have fun. And I then have to sit at a blank computer screen and just think and process, okay, how can I combine what I know, about engineering and aerospace, and knowing, okay, if it's going into space, it's going to have to survive the launch environments, the hot and cold, the vacuum of space, take those kind of aspects that my education gave me and combine them with the requirements, and sit in front of that very uncomfortable blank computer screen and create something. I usually start with the 3D model and take it from there into drawings, and then we'll get it fabricated. And by then, about a year has often gone by, but from when I first had to sit and be incredibly uncomfortable, and I still don't know if everything's all gonna fit together exactly how I wanted it to, and we'll go through the testing process of whatever I've built, make sure it comes to life as we've planned. But yes, being comfortable with being uncomfortable, being comfortable with failure, it's another one of those weird things that you don't ever think about you're going to have to do once you get out of school. It's like, oh no, I've got this now. No, you start right back at the beginning sometimes, but that's the exciting and fun part and the challenge part. And on that kind of same challenge part, we'd love to, I think we maybe have some questions coming. Is that?
So we do have one question so far that is, what is the most interesting thing you have learned both about studying radiation exposure and from advancing heat shields? I think this is more of like on the technical side, what you found fascinating.
Ooh. Do you want to go? You want to go?
Okay, so the most interesting thing I found.
I can go.
Go.
Okay.
Give me a minute.
I kind of have it easy on this one, because the actual most interesting thing I found is the technology that I'm working on, and kind of what's come inherent to that. So one of our biggest challenges to actually getting people on the surface of Mars is getting through the atmosphere slow enough that we don't crash land on the surface. Because the atmosphere of Mars is actually quite thin. And so you want to create enough drag as you're coming through. And drag is kind of that same idea as if you're driving down a car on a highway and you stick your hand out like this, and you can kind of, the air will flow over it, versus if you stick your hand like this and it immediately pulls you back. It's that concept. And so we have to do that as we're coming into the surface of Mars as well. We want to create enough drag to slow our spacecraft down. And so the technology that we're working on is actually a larger heat shield than has ever been developed before to try to create that drag. Because traditionally, heat shields are made out of ceramics or metals, and they can only be as large as your rocket diameter is. So it can only fit in that size space. What we're working on is actually a flexible and inflatable thing. So think kind of a bouncy house, only for space and in a heat shield type shape. And so we actually have, once the rocket fairing will pop off, the heat shield will expand to its largest diameter and come in and actually create the drag that we need to not crash, to actually land all of the life support that we're going to need to bring humans to Mars. So I think the most fascinating thing that I've learned is just that there are things that are really hard about getting to space, including small atmospheres. And we get to play with, that's one of these requirements that we get to play with and say, okay, how do we come up with something that can slow us down fast enough, that can get through, use that atmosphere to our advantage. And by doing that, we're creating an inflatable heat shield. And it's we've gone through a couple of ground tests, and actually right now our project is called Lofted, Low Earth Orbit Flight Test of an Inflatable Decelerator. So that's a mouthful. But the previous ones, you can Google it. IVRE3 was actually a launch on a sounding rocket, and you can see videos of it expanding. And so we're going to be doing that again, launching in about 2020, 2021, and we're actually going to go into orbit and come back in. And once it comes back in from orbit, it'll be the largest blunt body diameter that will ever come back into Earth's orbit. So it's going to be an exciting thing, and I'm sure that after that, I will have so many more fascinating things that I've learned to share with y'all.
That's very cool. So I'm going to talk about two parts of the radiation problem I think that I find very fascinating. The first is the physics of it, in the sense that you have this complex radiation environment in space where you have these very, very fast, heavy ions. So the nuclei of all the elements on the periodic table, largely. So these are complex nuclear bodies moving at very, very high speeds. They're very, very small, of course, but moving at very, very high speeds. When they interact with the nuclei in like an aluminum shielding on the outside of a spacecraft body, there's this massive cascade of particles. So the nuclei break apart. They break apart the cosmic ray part of it breaks apart, and the target part, so the shielding material, breaks apart. And this cascade of particles falls through. And particles are created out of the energy that is in that interaction. So the kinetic energy from the cosmic rays is converted into particle production. You get all these this massive soup of particles from just one simple interaction. This incredibly complex environment is created within the vehicle. And that environment, turns out, for very small shields, is actually more damaging. So a little bit of shielding is worse than no shielding at all in terms of the amount of energy, the dose that the radiation deposits within the body.
I know that.
And so it's because all those complex secondary particles that are created. So we have to be very careful when we're designing radiation shielding, so that we use the right types of materials to break up the cosmic radiation, and we have enough of it to dampen, in a sense, that environment, so that it's not worse or even as bad as outside. Of course, we can't live without just our spacecraft, but
small bit.
Small things. Sort of the other side of the problem, the biology side. The human body, so I'm a physicist, I like to boil things down to their most simple components and understand them at that level. You can't do that with biology. And all the biologists out there are laughing at me because they tend to do that to physicists, because we tend to oversimplify things. When you oversimplify things, you lose the biology part of it. So being able to learn to maintain the right level of detail and simplification in modeling biology is a constant struggle for me, and very, very interesting. Things that are difficult. That's why I became a physicist. I was interested in hard problems. And so this next chapter, as I start doing radiation biology and understanding risks from radiation to the human systems, is very interesting. So that's my answers.
Yes. And then also, what types of people have you worked with on these projects? Are they all people with the same backgrounds as you, or is there a diverse group of people working on?
So for me, on the research side, it's incredibly diverse. So within my field, space radiation is already multidisciplinary in the sense that it's the intersection of applied physics, pure physics, biology, engineering. All those things intersect. Mathematics, very important. So even just my small research group, we have nuclear engineers, we have mathematicians, we have radiobiologists, we have biophysicists, and that's just in the team that works on the small projects I have. That doesn't account for the people who are in charge, procurement. How do we get the resources we need? The people who buy the things for us, people who keep track of schedules, and managers who have to report up the chain. Every little project at NASA has got a huge amount of support available to it.
We can't get our work done
at
all without that.
There's no way I could go and have to, even the non-technical stuff, take away all the technical stuff. All the non-technical work that goes into making the technical work happen is extremely important. And it's people from all walks of life. It's people with all amounts of education. I have a PhD. I work with lots of PhDs. We work with lots of people who have masters, lots of people who have just had bachelor's degrees, people who are experts in understanding how to buy things for the government, which is extremely complex and difficult process. Seems like you should just be able to walk down the hallway to buy, or go to the store to buy the computer. That's not how it works. We need specialized equipment. How do you procure that specialized equipment in a way that's consistent with all the rules that we deal with in the government?
Yeah, I mean, that tends to be my life as well. I obviously, as an engineer, I work in the engineering directorate, so I am surrounded mostly by engineers. But as Ryan said, you are never in your own bubble. I'm never just with engineers. You have everyone in the project. But not only that, if you do actually just look into your bubble of, okay, I'm on the engineering side of this project, who do I have to work with here? Who's on my team? Well, okay, let's take my heat shield, for example. I'm in charge of the inflation system. So I'm in charge of making sure it actually inflates. To do that, I have to work with the electronics engineers to make sure that there's some system to be able to turn on the inflation sequence. I have to work with the thermal guys, both to make sure that it will re-enter the atmosphere and not burn up, but also to make sure that it doesn't get too cold before it goes in, to make sure the gas doesn't turn to liquid. So there's all different types of, even just within engineering, that kind of background. Sure. And I would say there's all different types of ages, also all different types of, I'm gonna throw this out there. I'm a female engineer. There aren't a ton of us here, but I'm never alone in that. And so I would say that there's, an incredible diversity found at this center and found within your team, both in terms of background, in terms of specialty, and in terms of, age, ethnicity, all those kinds of aspects to it, which comes into play when, as we talked earlier about the communications part, being able to take my mechanical or my aerospace or my inflation system and communicate to our electronics engineer that I don't just need an on switch, which, by the way, is what I thought that I needed at first. And you need a lot more than just a go switch. So it's being able to communicate that back and forth that makes working on teams both challenging, but also exciting. And when you kind of hit that rhythm of being able to realize that everyone is coming from different perspectives and bringing that to the team and realize that that is going to help you and not hurt you, that is when your team is just going to succeed so well.
Yeah, I think an important thing also on top of that is, especially with those large engineering projects, managing those systems. Like how do the people, managing the people and keeping everything straight, making sure everything happens at the right time in order, because
if we inflate before we go into the atmosphere, then, well, we're just floating around in space as an inflated object. That's not helpful.
Not gonna work so well, right?
No. So yeah, it's all of those, and even interacting with the launch facility. So I'm mounting something that's going to inflate on the top of a rocket. That can scare a lot of people. So I have to work with the facilities down. I think we're going to launch out of Cape Canaveral. So I have to work with them and make sure that I'm not going to blow up their rocket before it even gets to space. And so there's all these different kind of down to the minutia of where you're going to mount, how are you going to go. And so it's teams and teamwork is so critical to the work that we do.
Agreed. Any other questions?
Yes, so in terms of your inflatable heat shield, how do you inflate it and how do you keep it inflated?
Those are great questions. Part A is still what I'm currently designing. So we are going to, long-term goal, getting people to space. We are going to have to come up with a new technology to hold the gas, because that's a long ride to get people to Mars. If we're using this, we want something that's going to have kind of a slow burn and create enough gas over time. For re-entering just our Earth's atmosphere, we're actually carrying the gas, it's nitrogen, carrying those in big tanks on our spacecraft. And so we have to run those tanks through a number of different piping systems, pressure regulators. For example, the tanks are at 3,000 PSI, and our heat shield is going to be at 20 PSI. So figuring out how to get that pressure differential changed, how to make sure we're flowing the gas fast enough that it inflates within that time to get into the atmosphere, but also not too fast so that we get pushed too much gas into our heat shield and blow it up. Once again, this is a big problem for me, things exploding. But how we actually get it to hold it. So we've developed, it's kind of actually, the heat shield looks like inflatable pool toys, like the round, what are the round rafts? Like a
tube.
Yeah, tube, thanks. Look like inflatable tube that you float on in the pool. And we've actually stacked a bunch of those, actually 7 of those called tori, together to make it in this cone shape. They each get a little bit bigger. So each of those tori is going to hold a ton of gas at 20 PSI. And we've worked with, this is one of those secretive new technology things, with a new type of wrap design to hold everything together that actually is ideally not going to leak as it comes through the atmosphere. So the same thing as, you blow up your pool toy and you can kind of float in it for a while, and eventually it might start leaking and you might start slowly getting compression. And so we're going to be monitoring that actually as we enter the atmosphere. And if that starts happening, we'll open up the inflation system again, push more air into it, but it's going to hold it a lot on the way in. And once we actually land and splash down, we then have to get the air out of the tanks that we've now inflated it, because if there's still air in there while people go to pick it up, that's another hazard of something exploding. So we're actually going to, where we have systems within there to cut it off from the aeroshell, and we'll vent the tanks then once we actually enter Earth's atmosphere. Does that kind of answer the question? I think, did I hit it? Okay.
I have a question.
Yeah.
So the current thinking is for long duration to have some sort of chemical reaction from propulsion, or unknown, that actually is then stored and used as the gas? So
it's kind of a gas generator. So it's not, so propulsion will be needed. So we are not actually, we're trying to stop the thrust as we go into the atmosphere. So we aren't looking to create any kind of thrust with our motion. We're just kind of looking to create gas itself. So right now it is a slow chemical burn. So you'll have solid materials that when you ignite them, they'll slowly create a gas as it comes down, and we can flow that into the system.
Very cool.
So yeah.
See?
Learned something new. I've already learned about ions.
And then in terms of radiation, what is the difference in radiation that an astronaut might experience in space versus here on Earth, just going about their normal day?
Oh, great question. So space radiation is fundamentally different than terrestrial radiation.
Terrestrial meaning on Earth.
On Earth. Terrestrial radiation sources are natural decay of elements You might find one of the biggest ones for human risk is radon. So if you happen to live in places that have basements, you can have a lot of radon in basements.
Should I be afraid of my basement?
Probably not around here.
Okay.
If you happen to live in the upper Midwest, then yes, it's higher sources of radon.
Move. Just kidding.
Additionally, you can have radiation sources from nuclear reactors, and those are typically neutrons. And there's no neutrons in the space radiation environment. It's all charged particles. Another possible source of terrestrial radiation would be nuclear weapons, which are typically the radiation that comes off of them are photons, so high energy photons, gammas, and X-rays. While in space, the cosmic rays, so you have two sources, galactic cosmic rays, which come from outside the solar system into our solar system. They are all periodic elements, nuclei only, so they're fully stripped of all their electrons, and they're moving at close to the speed of light. You also have a source in the sun. When the sun has storms, it can erupt and push off huge masses of plasma. And that plasma then is accelerated by these internal magnetic fields created by the sun. So those storms are actually magnetic storms, and they erupt off and they carry a magnetic field with them. And then those particles, mainly protons from the sun, are accelerated by those magnetic fields up to near the speed of light again. And so they're extremely energetic and particle type rather than sort of neutrons and photons that you would find, or lower energy alphas from decay of particles on the surface of the Earth.
So it's the actual type of radiation particles are different, Earth and space?
Type and energies.
Type and energy, and space is worse for us.
Space is worse. Luckily.
Good note. Just want to make sure. I'm still afraid of my basement now. I don't know.
Don't be afraid of your basement.
Right.
It's not that bad. But it is a source of radiation risk to people. And there's also natural variations over the surface of the Earth. There's places that are 3 or 4 times more radioactive just from the rocks that they're built upon all over the Earth.
Cool.
Yep.
Where are those? Have you ever been to one?
I have not. No.
Okay.
I think I would.
He's not
go.
glowing, so I guess.
Not yet.
I'm sorry. That's still my idea of radiation. You glow.
Yeah.
He's very smart.
Unfortunately, there are no Incredible Hulks.
Well, not yet. Sorry. Do you have any other questions? I'm going real off on this.
We have 2 final questions. So
Okay.
The first one would be, what are some things that we should consider when we're wanting to launch something into orbit that you would consider a high priority?
Okay. You want to consider as you launch in orbit. It's not that I don't know. It's that there are just so many things that you want to think about. So we go through a series of tests, very specific ones usually that are the biggest gotchas of launching. So going anywhere into space, not just going into orbit, you will build whatever it is you're hoping to launch, and you do the basic structural stress analysis on it, making sure that it's not going to break down, and you build it well enough that you're going to hold it all together, and you do the thermal properties. So maybe you've wrapped it in some isolation or insulation, and then you go through a testing period before you can even get onto your launch rocket. And so those tests are usually vibration tests to make sure usually your launch is actually the worst vibration that it's going to see the whole time it's in space. Kind of as it goes up, you've seen the videos of astronauts kind of shaking a little bit in their seat as they go up, and your spacecraft goes through that as well. So you have to make sure it's not going to break off. And actually that was my first ever job when I got here. Someone handed me a bolt that had broken off of a spacecraft that was almost ready to go to space and said, "This broke, make it not happen again." And that was my first realization that this was going to be challenging, and I had to be okay with being very uncomfortable with not knowing what I was going to do. So vibration testing, you want to make sure it's going to survive launch, because if you can't survive launch, there's no purpose of even being in orbit, even being in space. We also go through a thermal vacuum, TVAC, to make sure that your spacecraft can survive, as I mentioned, the hot also the cold of space, depending on where you are in your orbit, if you're closer to the sun or if you're further away. And within that hot and cold, we also pump all of the air out to make sure that everything can still operate in the vacuum that is space. Make sure that your spacecraft can turn on, take whatever measurements it needs to do, facilitate any human life support that it's needing to facilitate. So TVAC is another one. And there's also a number, electromagnetic induction EMI testing. That one I'm not as familiar with, but I think it's more in your world of science and research, and I'm not sure. But I would say in what I've done thus far and what I'm the most familiar with, I'd want to make sure that it's going to survive the space environment, hot and cold, vacuum, and make sure it survives launch before I put it into orbit.
I agree. For the human side of the equation, I would, you have to make sure you have a way to create oxygen. You have to have a way to take out carbon dioxide out of your air. You have to be able to deal with, trying to say this delicately, but a toilet. You need a space toilet. You need to know what to do with the water and the solid waste and how to handle it. Everything that you need to survive on Earth that's provided by Earth, you have to replicate in space. And that's one of the biggest problems with putting people into space, is that replication of the things that we get from the Earth naturally. Water and oxygen are preliminary. So you have to design systems that do that, and they have to do it reliably and for a long time. So things like the ISS are actually incredibly useful for us understanding how to take next steps in space. So how do we go from, a platform that's very, very large? ISS is massive. If you ever get to see its physical footprint, it's larger than an American football field, which is mind-boggling. And so everything that goes up there is fairly close to us, right? It only takes a little while to get there and back. There's not a huge delay. When we finally send people to Mars, they're going to be, 18 months away. If something goes wrong, you have to figure out how to fix it with the people you have there and the things you have on hand. So you need to design systems that are quite robust. Like how would we handle a medical emergency with a crew that's halfway between Mars and Earth? What tools would you put on that vehicle to solve that problem? And that's stuff that's being worked on right now by NASA, asking those questions and solving those problems. So in addition to getting off the surface, when people are in the loop, it's a whole nother set of problems, in addition to all the regular problems it is just putting things into space. So it's, there's lots of work for lots of bright people to work on.
Yeah, and the human equation. I mean, there are so many things that we take for granted on Earth, like walking. In space, they're just floating around up there. So I believe astronauts need to exercise, 2 hours every day, just to maintain their bone density and muscle mass, so that when they come back to Earth, they don't have serious health issues. So all those things are needed if you're going to send humans to long-term in space. And a big one, if you're going to send humans up there, is to make sure that we have a way to get them back home. Right. So if we're going to Mars, that's one of the reasons why we're needing these bigger heat shields, because it's not just landing them on Mars, but we need about 20 tons more equipment just to even get them their life support and get them a way that they can get back home. So that's one of the big kind of gotchas of, okay, we're there, we can send them, they've got everything they need. Oh, right, let's bring them home and make sure that we're not just going to strand them out there Martian style. There are lots of things to think about, and it's kind of the fun task that we get to do in space.
We're very privileged to get to work at an agency that gets to solve big problems. I'm very thankful. I know you are too.
Oh, yeah. You said you had one last one?
Well, people just want to know how long you've been working here at NASA.
We actually officially started on the same day. Right. So we've been here. We didn't know each other then, and we came into the room together. But we've both been here officially as hired NASA civil servants for 6 years. it'll be 6 years in January. And then you were here as an intern before, though, or?
Yeah, so I once I got my PhD, I came on as a postdoc. I did 2 postdocs here, which is sort of like this job you have before you get a real job. It's kind of like an internship, but you have a PhD, so they can't call it an internship. And then I was also a research professor while I was here. And so then I got hired on as a civil servant.
Yeah, and we've loved every minute of it since.
Yeah.
Well, thank you. I know that this has been more than we could have expected, so thank you.
Well,
thank you for listening to us for this long.
Thanks for coming and watching us, guys.
And then remember, our next webinar will be on Monday, October 29th from 4 to 4:30 p.m.
All right. Bye.